This mini lecture is about free body diagrams. First, free body diagrams are used for identifying forces acting on an object with mass m. And the reason for using them is to focus on the object and then isolate the object and then identify the forces acting on it. Generally speaking, there will be two kinds of forces: non-contact forces, weight, Coulomb force. This is the attractive or repulsive force between two charges, or magnetic force. And the other class of forces are contact forces, examples of which are the normal force, the frictional force, and the force of tension. In, for example, a string when it's stretched. And the idea is to identify the forces and then draw them as accurately relative to all the other forces as possible. And so as an example, let's consider an object with mass m on a slippery plane. The subtext here is that there's no friction. And so in a static context, we saw that the coordinate system of easiest application here is one where you have one axis, let's say the x-axis, parallel to the plane, and the other, the y, perpendicular to the plane, as I've drawn here. And so we will look at the y and the x direction separately. And so you can see that the normal force is perpendicular to the plane, so there's no components that are required to put n into y or x component form. W, on the other hand, which is acting downwards here, W equals minus mg, we're going to compose this vertical down force into a force acting in this direction, minus mg cosine theta, that's perpendicular to the plane. It's counterbalanced with a normal force pushing back in an equal and opposite direction. And then down the plane, there's an unbalanced minus mg sine theta. And so to write these in y and x component, the y component forces would be n minus mg cosine theta. That would constitute the net y force, and that is 0 newtons since there's no acceleration in the y direction. So the plane is going to be, if there is any motion, the motion is going to be either up or down the plane, and there's no acceleration and no motion in the y direction. And so that allows us to make this conclusion. In terms of the x direction, we only have one force in the x direction, and it's this unbalanced minus mg sine theta force, so that is the net force in the x direction. F net x is equal to minus mg sine theta. And so now we can apply Newton number 2 and say that the acceleration in the x direction is the net force in the x direction divided by the mass. And that is minus mg sine theta over m, which is minus g sine theta. And so m will then accelerate down the plane with an acceleration equal to g sine theta. If theta is equal to 0, a is 0 meters per second, and the object will not accelerate down the plane. That's one extreme, and then the other extreme is if theta is equal to 90 degrees, that would be equivalent to making the plane vertical, and in that case the acceleration would be 9.8 meters per second, which is essentially free fall. And so one of the outcomes of this free body diagram for a slippery ramp is that by changing the inclination of the ramp, you can adjust gravity, the component of gravity along the ramp, by adjusting theta from a minimum of 0 to a maximum of 9.8 meters per second, and anything else in between, depending upon what theta is set to. And this is the technique that Galileo used to study gravity, to slow the 9.8 meters per second down with the ramp so that he could indeed study it and understand it with the tools that he had.